Okay.
Hi, this is Group 21's presentation for portable filtration systems for emergencies and remote areas.
My name is Emily Lopez.
I'm Hayden Redmond.
I'm John Barixa.
I'm Morgan Arona, and Dev couldn't be here for this recording, so he will be thrown in later, but he will still be in here. So the needs statement for this project, it begins with a lot of places they have problems with water. Like many places around the world would lack the infrastructure necessary to provide safe water, like safe, reliable drinking water. Like a lot of developing nations, they have a lot of economic limitations where they can't build a lot of large scale purification centers or a lot of places to have maintenance or pressure systems to provide water to people. And even when there's natural water sources available, there's a lot of pollutants and bacteria in them. Like this is a known thing. And beyond developing countries and other rural places, there's also similar challenges that are geographically limited. Like it's hard for a rural area to get water to, like you got to ship out the material it takes. You just got to bring in more stuff. And that requires a lot of logistics and it requires a lot of stuff that they don't have the money for. And this also extends to emergency responders and humanitarian aid groups because while they're helping, they can't bring in this infrastructure. So they need a way to provide water to people that are going through an emergency. And so our project will address this issue by developing a modular portable water filtration system that it can adapt to various environmental conditions, resource constraints, and user needs. By focusing on simplicity and reusability, the system aims to provide safe drinking water in situations where traditional purification methods are unavailable or unreliable. So the global water crisis, there's some interesting facts about it. Around 2 billion people in the world have unsafe drinking water like that they have access to daily. And this causes about 485,000 deaths a year from diarrheal diseases alone. Disasters like hurricanes and earthquakes, those cripple systems for weeks, sometimes even months if they can't get the money out there. And people got to keep drinking water, so it leads to drinking unsafe drinking water. And then there's also long-term problems like remote areas that just, like I said before, they don't have the money for it. And then there's short-term emergency gaps like bottled water, you can bring that, but you got to ship out pallets. Those are heavy and it causes waste. So there's problems right there. So for our problem definition and our design objective is to develop a modular filtration system capable of producing clean, potable drinking water under diverse field conditions. Our key goals are filtration for bacteria, sediment, and organic matter. It has to be easy to carry and easy to maintain. Like you got to be able to get around with it without it taking up tons of space, and it can't just break on you quickly. It has to be scalable for individual households or small groups. So it has to be able to be carried in small groups, such as packs, like when they're carrying it around, so that it's not like something that needs an entire vehicle or an entire team of system or entire team of people to set up an entire system. And it has to be operable without electricity or pressurized infrastructure. This means no pumps. It can't rely on electricity because of it either being in rural areas or too expensive or the infrastructure's down. So it needs a way that it can be used without relying on these things.
And for our analysis of alternatives, we came up with three different designs, each with different costs and each with different benefits. The first being a gravity-fed modular unit, which, as its name implies, it uses gravity as its source of filtering. We have a hand pump powered unit, which is similar to the gravity fed, but it uses a pump to pressurize, and then a backpack integrated unit, which is the best for general mobility. So for that first design concept, the gravity fed modular unit, the first thing to note as far as limitations go, it's really slow. We have it here for zero point 0.5 to 1 liter per minute. They're also a little bigger. It's just water slowly filtering down. And the main benefit of these is that there's not a lot of moving parts. They're really simple and they're super cheap, super easy to set up, and they are one of the more efficient ones. But it's that time that the time delay for waiting for the water that's the biggest downfall for those. And for our second design, we did the pump design, which is really just an upgrade from the previous design, except that it has a lot of moving parts now, which adds an added cost because that's something else that can fail. But it does come with the increase of speed. So more water more quickly. I would say this is probably the more mobile system compared to the other gravity system, but it's that cost and those parts and really the speed that makes this one the best one. And it's just a simple foot or hand pump, however the design goes.
The third design concept is the integrated backpack unit. This consists on a portable setup that combines a water filter inside a backpack. It is mostly designated for workers and hikers. Some of the advantages are that it is convenient since allows water filtration in one system instead of separate equipment. It allows quick swap cartridges so the switch filters can be done in a flexible way. Also, it is practical, which is designated to integrate with existing gear like hydration hoses, reservoirs. But we have to consider a few trade-offs. The first is that the system can be more expensive and complex to manufacture. Now I'll go over the concept of operation. There are different scenarios in which these concepts can be needed or used. One scenario that this can be applied is after a flood, where relief workers collect the water from a nearby stream. They pump it through the modular cartridge, filling contained with safe drinking water. The same cartridges can be reused in a gravity setup or swap for different filter media, and eventually the filter will reach its lifespan and need replacement. The system's sequences describe for different steps. The first step is the input, which is the contaminated water. The second step is the process, which uses different stages filtration. The third step is the output, which the water needs to be 99.99% bacteria free. And the last step is step 4, which is the maintenance, which will require to replace the cartridge after a certain amount of liters.
So the system requirements and design targets that we set up for this, we broke it down into a few different parameters here. So something that's important is our flow rate, which we have targeted as more than 1 liter per minute. We determined this because we want to have a high flow rate that accommodates all of our designs and all of our concepts, and for different type of scenarios that might need higher flow. We also aim for a bacteria removal target of more than 99.9%, which, as mentioned, is the EPA potable water standard. We want to meet that standard, so we actually have potable water, not just water that appears clear. Next, we want to have a weight of our design to be less than 2.5 kilograms. That accommodates the third concept primarily because we have the portability aspect that we can put in backpacks and integrate into existing systems and not add additional weight where unnecessary. Next is the service life. We want to have a longer service life so we don't have to replace quite as often. So we're aiming for a target of more than 500 liters per cartridge. This is, of course, a desirable trait because it reduces cost of replacing the system and decreasing maintenance. But even when we do need to replace the system or parts of the system, we're aiming for a quick replacement time and a quick turnaround. That way, people don't go without water, especially when these types of systems are really critical to life in certain areas. And then finally is the power use. We want to have a system that is entirely free from electrical power. Instead relies primarily on human power or gravity. That way it can be used in a variety of scenarios where electricity may not be accessible. Next up is kind of a breakdown on how it generally works. Here on the right, we see just a cross section of the filtration system, where of course we have water coming in from the top that's contaminated, and our filtration media following that. In this design, 2 different layers, and then finally we have an outtake of filtered water. For that design, we of course have our inputs of contaminated water and human effort. Like I mentioned before, we want to have this powered entirely by humans or gravity, no electricity. And then for our processes, as I mentioned, our filtration is going to be both mechanical and through absorption. So that way we have the physical or the mechanical filtering of larger particles like rocks and soil and dust and things like that through the filters. But then we also have types of filters that will filter through heavy metals and other bacteria and things like that to produce safe drinking water. We also, for our outputs, like I mentioned, the potable water, which is critical to the design, and then the waste contaminants are in the filter. For our control functions, we want to have user flow control to change the flow rate, and then also have a way to indicate when the filters need to be replaced, as they are an expendable part of this design.
Now let's take a look at the SWOT analysis for our modular water filtration system and explore the key markets we are targeting. Our primary market focus includes 3 major segments: disaster relief agencies, outdoor recreation, and military or emergency responders. Starting with disaster relief agencies, organizations like FEMA, the Red Cross, and UNICEF represent our main target audience. These agencies already rely on emergency supplies such as purification tablets and shelter kits. By introducing a modular reusable filtration system, we can help them reduce dependence on disposable items, lower resupply cost, and improve efficiency in the field. Next, the outdoor recreation market provides a large secondary opportunity with over 50 million participants in the US alone. Campers, hikers, and survivalists are always looking for reliable water purification solutions. Our system's lightweight and durable design, along with easy maintenance, makes it an appealing long-term option compared to single-use tablets or fragile filters. Finally, we see military units and emergency responders as a promising future market. These groups often operate in remote or infrastructure-limited environments where clean water is critical. Our rugged and modular system can easily adapt to fill packs or vehicle kits, supporting sustained operations while minimizing logistical challenges. Now let's look at the core strengths, weaknesses, opportunities, and threats for our product. Starting with the strengths, the modular design allows flexibility and easy maintenance. It's highly portable, adaptable for both field and emergency use. It can handle multiple contamination types through interchangeable filters, and some designs even operate without power, which is perfect for remote areas. However, there are few weaknesses to consider. The limited flow rate in gravity-fed systems can reduce efficiency, and regular cartridge replacements are needed for consistent performance. Manufacturing cost might be high initially, and transporting systems to remote or affected areas adds logistical complexity. Moving to opportunities, there is strong potential for partnership with major disaster relief organizations like the Red Cross, UNICEF, and FEMA. The expanding outdoor recreation market opens up millions of potential customers. NGOs working in rural or developing areas also present a humanitarian opportunity, and government or public health contexts could further support scaling. And finally, the threats. Established competitors such as Livestraw and Swire already dominate parts of this market. Supply chain disruption could impact cost and availability. Regulatory hurdles such as meeting EPA and NSF standards might delay market entry. And lastly, varying socio-political conditions in some regions may influence adoption. Overall, this analysis helps us understand where our biggest opportunities lie and what challenges we'll need to address as we move forward. By leveraging our strengths, particularly the modular sustainable design and strategically addressing these challenges, our product has strong potential to make a meaningful impact across both humanitarian and commercial markets. Thank you.